talk about this question here. Diagram of two atoms of beryllium is shown below. Identify which would have the lowest ionization energy. Explain why you state that. The beryllium plus or the beryllium? Andrew?
Beryllium plus.
Why do you say that?
It has less valence electrons.
Okay. I'm going to ask you a series of questions now. You ready?
Sure.
What is causing the attraction?
Wait, is each question worth 4 points or is it worth 1 point each?
I don't care about what points they're worth. I want you to answer the question. What's causing the attraction?
Protons?
Okay. How many protons does both of them have?
4 each.
Okay. So would the number of protons be affecting the attraction?
No.
Okay. No. All right. What other factor what's another factor, I should say? What's another factor that is affecting the attraction?
The number of valence electrons.
No. Kind of, but no. Not the way that you're thinking about it. What's another factor affecting the attraction? Okay. I open up to the class. What is one other factor affecting the attraction besides the number of protons? Lon?
Its place.
What?
Like where it's placed.
Elaborate on that a little bit.
Like it's like on the farther one rather than like closer.
Okay, so what is that we've been talking about over the last couple of days? What factor is that? Yeah, but what variable, I should say? What variable is that changing based on what you said? Lexi?
It's repulsion and you repel each other because they have the same charge, and that therefore lowers the ionization.
Okay, so we've got, I'm the only thing I'm asking is what factors? So you said repulsion because you've got the electrons repel each other. But I want to go back to what Lana was saying. What's the variable that she was talking about?
Distance.
The distance. So we have the charges. So I know it's not up here on the screen. I think it's up. Do I have it? I don't. Yeah, no, yeah, there it is. So I'm going to copy it. Paste it. So the nucleus, the number of protons, that's a factor. That's one of the Q's, right? What's the other Q have to be?
The electrons.
The electron. Now, so we're going to be talking about each electron individually here, okay? But the Q's are going to be, we'll call Q2 plus 4. Q1 is going to be -1. Okay? Now, what are the other factors? Distance. And, as Lexi said, repulsions, right? I'm going to get to that one here in a second. What is the attraction between the nucleus and B and C relative to each other? See, equal, okay? About equal. Why? What's not changing here?
The distance.
The distance. It's still plus charges and distance. Everything's staying the same. So the distance between the nucleus and C is the same as the nucleus and B. Distance isn't changing. What is the relative ionization energy of A compared to B and C? Because we just said B and C are approximately the same. Why?
Because it's farther away.
It's further away. That's the primary reason. Now we're going to get to Lexi's reason. Okay? So of these two are the same thing, right? Except this has an extra electron, right? Now, diagram, I'm going to read it again. Diagram of two atoms of beryllium are shown below. Identify which has the lowest ionization energy. Let's start off with just this atom right here, beryllium plus. Which one of these electrons would be the easiest to remove? A. Okay, now come over here to this. Which electrons, plural, would be easiest to remove? A and D. And the attraction between the nucleus and A and D would be what? The same. So the attraction for the nucleus for A would be the same as the attraction for the nucleus of D. But is the attraction for the nucleus of this A the same as the attraction to the nucleus of this A? In Lexi?
No.
Why?
Repulsion. B and A are both negative, so when they repel, it like kind of takes away some of the attraction between A and the nucleus.
Repulsions between electrons weaken the attraction. So, when you're approaching these questions, you want to you break it down. Look to see what are the factors that are affecting attraction. Distance and charge. That's this. But we also need to then bring in repulsion once you take everything else into account. Questions? So repulsions will weaken the attraction. They'll lower that ionization energy. It's not drastic, but they'll lower it a bit. Questions? Yeah.
There was another question on the quiz, and it was like, if you shorten the distance between the nucleus and the first shell, what would happen? And then, I didn't understand what that one was asking.
So if you decrease the distance,
It's like you decrease the distance, so the attraction between the electrons in the first shell and the nucleus would increase, but then also it didn't, the answers listed, I didn't know which one was supposed to be it, because, didn't make sense.
So on this one, it was number 3.
3, yeah.
So if the distance from the nucleus to the first shell were decreased. Forget the, so here's something you guys need to develop, not just this year, but in the future. Multiple choice questions become layered somewhat, okay? You're gonna move away from literally having 3 answers out of 4 be wrong, explicitly wrong, and 1 answer be definitely right, and you're choosing the right answer. You're going to be moving to possibly all the questions looking right or being stated in a way that make it sound like it's right, and you got to choose which one is the right one. So let's look at each of these and eliminate based on what we know.
It wasn't D or E because electrons don't attract each other.
Exactly, okay? So, the attraction of the nucleus, let's just stop there. Is that part of the statement a true thing? The attraction to the nucleus, is that a true part of that statement, okay? The attraction of the nucleus for electrons B and C would decrease. Would decreasing the distance decrease the attraction?
No.
That's not an answer then. Right? So we got to chop it up. B, the repulsion of the nucleus. Is that part true?
No.
Stop. That cannot be the answer. The attraction of the nucleus, is that true?
Yes.
Okay, let's look at the rest of it. The attraction of the nucleus for electron A would remain the same. Did we do anything to the distance of A?
No.
So that would stay the same, right? That's your answer. We got multiple layers here. You have to analyze that whole thing to be able to tell what's going on. Because again, we get to this equation right here. This V equals K Q1 Q2 divided by D. And in that atom, the equation that described, or the equation we would use would be V equals K times -1 times +4 and whatever that distance is. And that did not change. For B and C, they would both change the same way, right? Let's look at the other answers, okay? The attraction between electron A and B. No, there is no attraction between electrons. There's always repulsion between electrons. The attraction between electron A and C. No. Here's the thing, the way it's stated makes them sound like they're right. Okay. Who's got questions? Yeah.
Can you go over number 2 as well?
Oh no. Okay, hold on. You'll understand why I'm trying to get these out here in a second. If the number of protons were changed to 3, if we're looking at attractions, what would happen to every single one of them? Decrease, because our equation is that V equals KQ1, Q2, and we're changing Q and lowering it. If that's the only thing we changed, distances are going to stay the same, the charge of the electron is staying the same. If we're changing that value for the nucleus, then all of the attractions have to decrease. So if I go back and I put those answers back in now, uh-oh. There we go. Would the attraction for B and C decrease? Would the attraction of A decrease? Would the attraction of B and C increase? Would the attraction of A increase? Would the attraction of all electrons decrease? So this and this and this is going to be correct, but this is more correct. Because it's not just affecting A and B, it's affecting C as well. All of the electrons are being affected if you change a nucleus. Everybody all right? Who's got questions?
Will number 5 be curved?
What's a curve?
A curve.
A curve?
I forget what it's called. Is it curving a test or curving a test?
I have no idea.
I
dude.
forget.
I
what
have
the
no
name is.
idea.
The only tests I will ever curve are my AP exams.
Okay.
I have no idea how that would work in this class. I will never make students compete between each other for a grade. Never. And that's what curves do. They cause students to compete against each other for a grade.
Can the V be negative in the equation?
Yes. It is in all of these, it's negative.
Okay.
It can also be positive. And really the only one that would relate to that would have been this question 5 where we were talking about the repulsion between those two electrons. Okay? Questions? Deep thoughts, right? You gotta think about it. This isn't just memorize little facts and stuff. This is what makes this class different. You gotta think deep about all the different factors that are in play. Okay? And everything again revolves around this equation. Okay? Who's got questions? Anybody? What? Jeez. Okay, this is not working. All right, development of a shell model, hydrogen and helium, right up 3 possible. Did we do this one last time? Or was it the previous slide that we got to?
I think it was
This was the one we stopped at, right?
yeah.
Okay. So, in our hydrogen and helium, so provide a possible explanation why the ionization energy for helium is less than double for hydrogen. The previous slide, we were looking at why should it be approximately double. And that goes to the nucleus. Between hydrogen and helium, we double the number of protons, which means we're doubling the number in the numerator of the V equals KQ1, Q2 divided by D. right? Nod or shake. Okay. So if you double the numerator, what are you going to do to the answer? You're going to double. So by double the number of protons, we should see a doubling of the ionization energy, because we're going to see a doubling of the attraction. Now, as you can see, that's not the case. And one of the reasons we gave was what? Distance. The distance between these electrons in the nucleus is larger than the distance between this electron and the nucleus. And if you increase the distance, you're going to do what to the attraction?
Decrease it.
Decrease it. Which means the ionization energy is going to decrease. And what was the other reason?
The electrons repel each other.
The electrons repel each other. And if the electrons repel each other, that's going to decrease the attraction compared to what we would expect and make it easier to remove it.
So when you double the number of protons and you still have one electron, isn't the ionization energy double that of one with compared to one with one proton and one electron? But when you have two electrons and two protons, the ionization energy is not exactly double.
Correct. Because we're always the thing about this, so when we plug into this V equals K, Q1, Q2, D, we are always going to treat this as one electron. Okay? So even though helium here has two electrons, we're looking at each electron individually. So it's like we're comparing those and those. And because this has double the number of protons, we should expect a doubling of the attraction. Because whatever is true of that electron is true of that electron. Okay? Because we're always looking at it as one electron and how is it interacting. Everybody okay? Write out the three terms for helium. So for that atom right there, if you want, we can designate this A. And we can designate this one B, if you want. Or three equations that describes the interactions between those particles. You got a minute?
You make K1.
Sure. Or you can just leave it as K. Can't be -2. And we always do just one electron. I'm going to call this V sub A. Somebody finish it for me. Ava?
Positive 1 for K, negative 1 for an electron, and and +2 for the nucleus, divided by 31.
Oh, yeah, because I do give you the radius, don't I?
Yep.
Ah. Mandy?
V equals K times -1 times -1 divided by 62.
Let me change something. Maddie?
V equals K times -1 times +2 over 30.
Okay. So, these were the same. You remember doing this, right? I think this is the second time, or yeah, this is the second time we've done this. Because last time we did it, we had it was the last slide in the previous set, where we had a 2+ in the middle, we had an electron on the left, it was 300 picometers, and we had an electron on the right, it was 400 picometers, and I asked you to do 3 equations. This is 3. This time around, though, these 2 electrons, A and B, are both attracted to the nucleus with the same attraction, meaning that they would both have the same ionization energy. Both of them, though, repel each other. Both of them would still have the same ionization energy, but this is why it's not double what the ionization energy for hydrogen is. Okay? Who's got questions? Lana?
For the one that was between the A and B.
Yes.
Isn't that it's -1?
Because the charge of each of these is -1. And we're doing a comparison between those charges. The only thing that's not going to be 1 is going to be our nucleus. And the nucleus we're always going to take as the charge of how many protons it has, because all the protons are packed rolled and they're in one little spot.
So how would we find the ionization energy just from, without you writing it out, and obviously we get K, and then we get the diagram of what it is, or just a description. How would we find 2.37?
You don't need it. We don't need to know what the actual numerical value is.
But how would you?
Well, you'd have to know K and D.
We do.
Right. But we don't have them for every scenario.
But how would you get that final answer?
Just plug them in and chug.
Yeah, but you have 3 different.
What do you mean 3 different? Oh, you mean what's the final ionization energy? Oh, okay, I understand what you're saying. You're not going to get that from that equation, at least easily. Okay. That's why we go through and actually go in and measure them. We could make a pretty good approximation, but until you actually do the actual measurement of it, that's all it is an approximation.
What's the measurement of it?
To go in and actually measure how much energy does it take to remove those electrons. Lexi?
If you have an element and on its outermost shell, there's let's say 3 electrons, and there's another element, the same element that has 2, so the one with 3 on the valence of what's outermost shell is going to have less ionization energy than the one with 2.
With some qualifications, yes.
Okay.
Okay? because life isn't as simple as that always. Based on what, but kudos, because your reasoning makes absolute sense. The more electrons you get in the valence shell, I know we haven't talked about that, but the more electrons you get in the valence shell, the more repulsions you have. And if the more repulsions you have, you would expect the ionization energy to increase or decrease, but get easier, because the repulsions are going to make those electrons not attracted to the nucleus as much. So you're absolutely right. There's some nuance in there that we are going to have to look at, though. Okay?
So like, as a hypothetical, if you had like 1,000,000 electrons, would that
That's a
just
lot of
like,
electrons.
yeah, would that just like end up having, like a repulsion that just have those nucleus, the nucleus is like a hydrogen nucleus, and it just like falls apart?
Well, the protons don't just fall apart.
No, I mean like the atom would fall apart. Like the proton would still be a proton, but all the electrons would just end up.
Oh, the electrons have no effect, have nothing to do with whether the nucleus is staying together or not.
No, I mean the atom. Like the nucleus would still stay together with protons and neutrons, but like with the electrons just all repel each other.
They're going to repel each other, but they're going to. What's going to happen is, so 1,000,000 electrons is extreme. Electrons are just going to start flying off until when?
There aren't enough to repel it. Like, so you run out of repulsion.
You run out of repulsion enough to cause them
Yeah.
to want to run away, right?
Okay.
Because once the attraction gets, once the attraction is strong enough to hold them there, then they're going to stay.
Okay.
But I understand what you're saying. If you have a whole bunch of electrons, but let's look at it the other way. You have an atom. It's neutral. Are electrons going to come into it?
No, because it's balanced.
Well, they could though.
Well, yeah.
Are they going to do so easily?
No.
And is there a limit to how many are actually going to come in?
Yeah.
Yeah, because there's going to be a limit to how much the repulsion is going to build up. Because if an electron comes in, why would it come in? Because there's an attraction. It's attracted to the nucleus. But you're also adding to the repulsions between the electrons that are already there. I like your, Lexi, I like both of you. I like the direction you're thinking with those. Because that's the kind of thing here that we want to do. Okay? I don't want to do that. We've talked about it enough. Okay, so this is where I want to come back to the development of the shell model. Because in your middle school science class, you were told that how many electrons are in the first shell? 2. And you just accepted it, right?
Yes.
And your middle school teachers are probably just fine with just having you accept it. I am not. There's a reason for everything, okay? So, all these statements kind of summarize what we've talked about. Because the helium nucleus has a charge of 2+, we expect that the ionization energy to remove an electron approximately the same distance would be approximately twice hydrogen. And that's what we see. There is a slight difference, and we have taken into account that repulsions are going to make that lower than what we would expect. Okay? So, last statement there. Within our shell model, helium consists of a nucleus surrounded by 2 electrons in a single shell. Now, we're going to have to approach this as a thought experiment because you already know what the answer to this next question is going to be, but this helps us answer the why are there only 2. So you ready to go in this with fresh mind? Okay, get yourself prepared then. You got 5 seconds. 4, 3, 2, 1. So if we're going with a shell model, then we're just going to, in science, you go with what works until it doesn't work anymore. So we have a shell. For helium, it's got 2 electrons in that shell, all right? Lithium's the next element on the periodic table. Let's put that 3rd electron that lithium has in that shell. If all 3 electrons in lithium were at a distance approximately equal to that of hydrogen, which of the following values would be the better estimate of the ionization energy? 3.6 or 0.6? Ava?
3.6 is if you have the same distance, but you have some larger, the 3 in the numerator is still gonna end up larger, because you're not dividing by anything bigger.
Right. So if they're same distance, all we're changing here is we're saying that we've got, oh crap. There we go. We got V equals K, -1, because we're still talking about electron, right? But this time around it's +3. Between hydrogen and helium is a +1 to +2, which was how much change? A 1 to 2 is doing what? What am I I'm doubling, right? Well, if I go to 1 to 3, what am I doing? I'm tripling it. So we're saying here, K we're going to stay keep the same. D is going to, is it going to be close enough to the same? So if we were to add a 3rd electron and it was to go in that same shell, we would expect the ionization energy to be about 3.6, about triple what hydrogen is. We okay with that? Everybody understand this statement? Brooke?
I don't. So, alright, by distance, what do they mean? Do they mean the radius, or do they mean
Yes.
the distance between what?
The radius.
Okay,
So how far is the electron away from the nucleus?
yeah.
So if we've got, for hydrogen, and this is for lithium, okay? For hydrogen, we'd have -1, +1, D, right? And I can't remember what it was.
31.
No, that's the distance. What was the ionization energy for hydrogen?
No idea.
Scroll back a couple of slides.
2.37 mJ/mol.
That was helium.
That's helium.
Okay, never mind.
1.31.
1.3, I'll just call it 1.3. Okay? So that's the ionization energy for hydrogen. So if I've got this, we would expect the ionization energy to be what?
Well, you already said it. It was 3.6. Triple it.
But triple that would be what?
Well, 3.6. Well, 9.
3.9.
And
But
then-
why are we saying 3.6? What are we taking into account? Repulsions.
But why? Okay. It's the warning, but like, why is it triple? Because I know the protons are triple, but
That's it.
doesn't the radius stay the same?
That's what we're saying. Assume the model for the shell outside of, if all 3 electrons of lithium were a distance approximately equal to that of hydrogen. So we're saying that D
Oh wait.
is staying the same.
Oh wait. It's the ionization energy. Okay. Yeah.
What were you thinking?
No, I'm thinking of something.
No, what were you thinking? Because I'm
I don't know what I was thinking. I think I was thinking in terms of like circumference for whatever reason.
okay.
So
all
I was
right.
like, why is it tripling? Yeah, I'm sorry.
No, I got-
That
no,
was
no,
a
no,
waste
that's-
of time.
But as a teacher, I'm curious as to where your misconception came from, because it helps me help others.
It's like, sort of like the diagram, I think, because I see that there's like distance between the three.
So you're looking at these?
Yeah,
Okay.
because,
Are you in geometry class?
no.
Okay. Yeah. We're not looking at the distances between the electrons.
I'm just,
We're almost exclusive, except to take into account that there are repulsions.
yeah.
Our primary is looking at what's the distance between the individual electron and the nucleus. Okay, Abby?
So how do you know the distance is doubled?
How do you know when the distance gets doubled? Hold off on that. Okay? We're probably going to be answering that here in just a second.
So like, if V equals potential energy,
Yep.
then what's stopping it from like becoming energy, like kinetic energy? Like what's stopping it?
What do you mean stopping it?
Like, if it's potential energy, why hasn't it turned into kinetic energy and something happened?
Okay, so, and this is where we run into the problem where the only energies you've been introduced to are potential something where its position is, and kinetic energy, how fast is it moving. There are other there's many different types of potential energy. In this case, it's the potential energy that's associated with the attraction.
Oh, awesome.
Okay, so there are many different types of exhibiting energy. Kinetic is the one that you're most familiar with and what you guys have been introduced to. Lexi?
I understand the statement, but what does this prove? Does this just prove that repulsions cause like decrease in ionization energies?
Say again?
Like what does this prove? Like this is.
Oh, okay. We're getting there. Getting there. Getting close.
So it's never exactly like doubled or tripled because of repulsion?
Exactly.
So
So
this
when
is
you
like
add more
exactly-
electrons, you're going to increase the repulsions, which is going to decrease the attraction a little bit. It's nowhere close
Just a
to.
little bit though, right?
It's just a little bit.
Okay.
Yeah, it's nowhere close to being. So if I were to triple it, it's not going to reduce it by a third.
Okay, that's, yeah.
Okay. So go to slide 2. Scroll back up. It's a table. It's got all the different ionization energies. We said this. Based on all the data or that we have up to this point, if we have a third electron here, we should expect an ionization energy of about 3.6. Is that the reality? No. We don't get that. We get a value of 0.6. So this is the reality. This is how science works. You go with a model until it doesn't work, and then you revise that model to make it to explain what you have observed up to that point, and also address what you are now observing. So between hydrogen and helium, they double. Okay, we got 2 electrons, same shell. Go to lithium, put that third electron in the same shell, that model doesn't work. Why does hydrogen have, or why does the first energy level only have 2 electrons? Because our experimental evidence shows us that it cannot. There's no way that we can explain the model of the atom and have 3 electrons on that same shell. And Abby, I think this might be where it's answering your question. So a new model of lithium with 2 electrons in a shell like helium and a third electron in a shell further away from the nucleus is proposed. Does this account for that large decrease in ionization energy?
Yes.
Yeah. So we go back to that very first slide, or the second slide. I tell you, I'll go back there again, so I can re-explain. We're talking about the first ionization energy. I know I've just been saying ionization energy, but when I say ionization energy, we now kind of mentally insert first ionization energy. And the first ionization energy is the minimum amount of energy, right, required to remove an electron. Now, in this diagram, which electrons would be the hardest electrons to remove? Which one would have the greatest attraction? A, B. Okay? But C is going to be easier to remove. So a model where we've got these 2 electrons in the first energy level, and then we add the third one in another energy level or shell, this takes care of that problem.
So first ionization energy usually applies to whatever's furthest away from the nucleus.
Always applies.
Okay, always. Would you be able to take out one of the electrons right in the
Yes, you
first
can.
shell
Yes, you
before you
can.
get rid of? Okay.
Yes, you can. And we are going to talk about that later. Yes, absolutely. Okay? Which becomes really important for understanding our structure of the atom. Using Coulomb's equation, provide 2 to 3 different reasons why this would be a better model. Give at least 2 calculations for it. Time-wise, I think you guys can do that. You can make 3 equations, right? Actually 4, but there'd be more than that, right? We get one equation that would describe these 2. We have one equation that describes that. But then we'd have equations that describe the interaction between all the electrons, right? And now it just becomes ridiculous. This is why earlier I said we're just going to think of it as the more electrons you get, the more repulsions there are. But even though there's more repulsions, they are not going to be greater than the attractions for the nucleus. Are we okay with that statement? Okay, assuming the radius for the first shell in lithium and helium are approximately the same, Ava, you just asked this question. Assuming the radius for the first shell in lithium and helium are approximately the same, which will have the highest ionization energy for electrons in the first shell? So these 2, which one's going to have the highest ionization energy for the electrons in the first shell?
Helium, because you don't have C repellent in it.
Oh, time out. If these electrons here, this electron and that nucleus are about the same distance, and that electron and that nucleus are about the same distance, which of these electrons is going to be harder to remove?
Oh.
Why?
Because there's more attraction, because there's more protons.
Exactly. In this lithium, the attraction for similar, okay? The attraction for similar electrons has to be greater for all of them in lithium because we got more protons. Now, we don't have an electron similar to electron C in lithium and helium, but in our first shell, we do. So these electrons would be harder to remove than the ones in helium. Questions? Somebody tell the class, what is happening? Brooke?
A and B are repellent
about all there is to say. Now, is A repelling B as well?
Yes.
Yeah, there's repulsions between all the electrons. Okay. So here I've got a listing of our ionization energies, and we see that between hydrogen and helium, it went up, and then we got a significant decrease, right? And then we add electrons, so as we go across the periodic table, we keep adding electrons. So lithium's got 3, beryllium's got 4, 5, 6, 7, 8, 9 electrons. 10 electrons, and we can see what use is that? I have no idea what use that is. We can see that from here. Oh. They all went up, right? And we don't see it doubling or tripling or anything like that, but they're all increasing. Because what are we continuing to add besides electrons? Add protons. And if you add more protons, what's going to happen to the attraction? It's going to increase. Okay, we get to neon. Remember your little projects you did in middle school where you had like all the circles and the dots, right? You know what I'm talking about, right? Lexi?
Or you just pointed out that there's a decrease between beryllium and boron.
Remember I said there's nuance in there, right?
Yeah.
We'll come to that later. I like your attention to detail though, right? Because you're right, there is a little bit, there's a decrease. There's a reason for it though. There's always a reason for it. We just have to figure it out, right? So, we got neon. It's got 2 electrons at first energy level. Neon's got 8 electrons in the second energy level. Huh, does that sound familiar? I mean, you were told there were 8. Why can't there be 9? Because the experimental evidence says, no, it can't be 9. Because what happens when you get to neon and then you go to sodium? You guys, well, no. What happens to
The ionization energy.
decreases a lot, right? You're going from 2.081 down to less than 0.5. It's decreasing a lot. If we had our 9th electron go in here, what would we expect this value here to be?
Higher.
Higher. Now, we're not going to say how many times higher because that we can't do that now. Our atoms are too complex now with the number of protons and electrons to say it's going to be doubling or tripling or quadrupling. But we can say with confidence that if we had an 11th electron and we put a 11th proton, and we put our 9th electron in this shell, that ionization energy should be higher. That's our model. Model says 2 electrons. We got another shell, second energy level. We keep adding electrons to it. Oops, doesn't work anymore. We get a significant decrease in our ionization energy, which explains or helps support the idea that we have multiple shells in an atom. So if we have this electron, this 11th electron, in a new shell, that explains the significant decrease. Abby?
So back when we were talking about light,
not gonna happen. Got no place to go. But could this electron go up to the third energy level? Yeah, there's room there. Okay. Questions? So using the data provided, we can see a shell added going from helium to lithium. Between what two elements do we see significant change and therefore new shells? So, shell 1. Let's start us off there. Where's our next shell encompassing? Marzier?
Between neon and sodium. Like, so the next one would be from lithium to neon.
Where's next? Road?
From sodium to argon.
Now, this is where I'm going to pause for a second and say, this is why this is why most of the time you're taught that there are only 8 electrons in shell 3. And in shell 3, there's not 8 electrons. There's 18 electrons. But it's not that simple to see unless you look at the periodic table. The little short part in the middle of the periodic table, how many wide is it? Ten. We just said third energy level holds 8, but I just said it holds 18 because 10. First energy level holds how many electrons? Look at the periodic table. Is there a part of that table where there's 2? Yeah, the left-hand side. There's 2 columns, correct? Okay. Little hint, as we will see here in the near future, all of the answers are on the periodic table. Okay, next set. What's that?
It's kind of just everything else is just confusing recently.
Yeah, so we go from potassium to krypton is our next kind of set, right? How many elements is that? 18. There's a reason for that. A lot, no, 18. It was specific. That's a perfect stopping point. Perfect stopping point. So class, as you're packing up, quick summary. We've got shells because we've got specific energy values that tell us that they have to be specific shells. Just go through notes, have questions ready to go for Monday, and I'll see you Monday. Have a good weekend.
The following students, please come to the main office. Coulomb, Sheikh, Mallory Woodstock,